Hi everyone, welcome for joining our MDPI International Day of Light webinar. So I'm your host for today, Shun. So just a reminder that the webinar is being recorded and the recording will be uploaded to our webinar's website as soon as possible. And if you have any questions for our speakers, please type it in the Q&A box and they will answer it at the end of this webinar. So I will start the webinar now. So a little bit about MDPI. So MDPI is a pioneer in scholarly open access publishing, and we have supported the academic community since 1996. So we currently have 422 diverse and open access journals, and we are working with more than 115,000 academic experts to provide high quality service for our authors. So this is the participating journal, Applied Sciences, for today's webinar. So Applied Sciences provides an advanced forum of all aspects of applied natural sciences. This journal covers all aspects of applied physics, applied chemistry, engineering, environmental and earth sciences, and applied biology. It has 5 broad subjects and 32 narrow sections. So this is the related special issue to today's webinar. So we have three special issues from energies, solar energy resources, technology, and challenges, advances in molecular optoelectronic devices and sensors. And from inventions, we have recent advances in visible light communication and optical wireless information systems. We have 2 special issues from biosensors. The first one will be nanoparticle-based photodetectors and biosensors. And the second one will be electrical or optical biosensing and regulating technology. And from technologies, we have the topic collection called electrical technologies. And from applied sciences, we have advanced studies in optical imaging and sensing, state-of-the-art in silicon photonics, advances in optical and optoelectronic devices and systems. And from sensors, we have towards optoelectronic technology from basic research to applications. And lastly, molecular optoelectronic sensing devices and techniques. So if you're interested in finding out more about our special issues, you can just search Applied Sciences MDPI. So a little bit about International Day of Light. So the International Day of Light is celebrated on 16 May each year. So it is the anniversary of the first successful operation of the laser in 1960 by physicist and engineering Theodore Maiman. This day is a call to strengthen scientific cooperation and harness its potential to foster peace and sustainable development. So the study of light has led to promising alternative energy sources, life-saving medical advances in diagnostics, technology and treatments, light-speed internet, and many other discoveries that have revolutionized society and shaped our understanding of the universe. So with that, we have invited 2 renowned researchers in this area. We have firstly Dr. Patrice Genevet, who will be presenting on topological metal photonics, and Professor Dr. Lorenzo Pavizzi, who will be presenting on neuromorphic silicon photonics. So a little introduction about our first speaker, Dr. Lorenzo Pavizzi, who is a professor of experimental physics at the Department of Physics of the University of Trento. So his research activity concerns the optical properties of semiconductors. And during the last years, he concentrated on silicon-based photonics, where he looks for the convergence between photonics and electronics. He is interested in active photonic devices which can be integrated into silicon by using optical nonlinearities and modified material properties. His interest encompasses also optical sensors or biosensors and solar cells. So he founded the research activity in semiconductor optoelectronics at the University of Trento and started several laboratories of photonics, growth and advanced treatment of materials. He was also the first president and founder of the IEEE Italian chapter on nanotechnology, and he has a director 42 PhD students and more than 48 master thesis students. And moving on to our second speaker, Dr. Patrice Genevet, who is the recipient of several awards, including the highly cited researchers by the Web of Science every year since 2018, the ERC Starting Grant 2015 on Functional Flat Optical Components and Applications, the 2017 MA Cotton Prize from the French Physical Society, the 2019 ERC Proof of Concept, and the 2021 Fabrice de Gremont Prize from the French Optical Society. Dr. Patrice Genevet's research activities concern the development of optical metamaterials, passive and active metasurfaces, and their applications, and integration in optoelectronic devices. He owns 6 patents, more than 100 publications, and with a H index of 48 from Google Scholar. So before I pass the time to our speakers, just a reminder to our participants that if you have any questions for the speakers, you can type it down in the Q&A box, and if you can indicate the name of the speaker so that at the end of the presentation, they will be able to answer them accordingly. So for now, I'll pass the time to Professor Dr. Pabisi. Professor, you can take over now.
I apologize, but according to the schedule, Patrice should talk first.
Oh, yes. Right? Sorry about this. I'll pass the time to Dr. Patrice. Sorry about this.
No problem. Let me share screen. Here. I need to switch, I guess. Okay. I think it works, right? You should see yes. The main. Okay, fantastic. So, well, I mean, thanks everyone for participating to this webinar today. Yes, my name is Patrice Genevet. I'm a researcher in CNRS, working at CNRS, in a laboratory called the Centre de Recherche sur l'hétéroépitaxie in the south of France. And today I'm going to speak about our recent work on metaphotonics and discussing a bit physics and the fundamentals and showing a bit some application of metasurface. So before to start, I would like to acknowledge all the members of my group, and in particular, Rémi Collomb here, Elena, and Renato, that are the 3 main persons behind the work I will be presenting. I would like to thank also the funding agencies and also mention a few names of the collaboration, industrial collaboration that we have on this topic of metasurface. Okay, so I'm not going to talk about all the research that is done in my group. I selected 2 these red boxes here, 2 subtopics. My group is working on metasurface and essentially starting from fundamental concept where we are studying the response of nanophotonic system, the scattering properties of nanophotonic system, and use these scattering properties to fabricate optical device, optical components, which we call metasurface. For wavefront engineering, we can control with this metasurface the phase of light. We can make device achromatic, eventually control the projection of light, including its polarization. We can integrate it into optical system to compensate, for example, for aberrations. And we are working also on active metasurface, but today I will speak only about this concept of topological metasurface that are fundamental physics used to design this component, and then an example for application of metasurface in a light imaging and ranging system for LiDAR application. I start with a very brief introduction. I'm sure that you're aware of this concept already, but you know that when you shine light at an interface that's separated two media, the light is generally refracted at an angle which is fully determined by the refractive indices and the incident angle. So now you see, if you start depositing here along these interfaces an ensemble of nanostructures, as shown here, and you design these nanostructures such that their relative response, phase response, for example, varies along the interface, you see that the light which will be re-emitted or diffused by all of this structure can vary from neighboring to neighbors in the form of a gradient here, for example. If you design it to have a response that varies in the form of a gradient, you see that the secondary wave emitted by each of those emitters now appears to be dephased, and that provides, if you want, if you take the envelope now of the actual transmitted wavefront here, you end up by getting a beam that is propagating in a direction which is fully controlled by the nanostructured array. So the presence of a phase gradient here along the interface can be used to direct or control the refraction of light at any arbitrary direction. This is what we showed back in 2011 when I was a postdoc in Professor Federico Capasso's group, using these metallic V-shaped antennas, where you see that the light here transmitted in the forward transmission direction from structure to structure varies, and between the first and the last element in this period, you see that you have essentially a wavelength of a phase delay, right? So you have a gradient of phase retardation, which is used to essentially beam light in a controlled direction. This brings to an expression for the law of reflection and refraction that becomes generalized, where you can now control the transmitted angle θ2 here simply by controlling the actual phase gradient of your interface. So you have a generalized version for the law of reflection and refraction. So we've been working since a while on this concept, and this metallic structure now are replaced in my group here using a dielectric material. We are fabricating this metasurface using gallium nitride material to work at a visible wavelength. We are using dielectric structure to fabricate this metasurface to provide high efficiency and function operation in the actual visible wavelength range, right? So with this device, we can make lenses, we can make various type of component operational at a wavelength that is of interest for humans, which is visible wavelengths, obviously. So as I say, a brief introduction here, the vision is that instead of relying here on a material that is shaped and that has a fixed refractive index and is shaped so as to control the wavefront of light using volumetric material, then we can fabricate now optical component, meta lenses, meta collimators, and different type of component directly at interfaces. We can reduce with that the thickness of this material to down a few hundreds of nanometers. So in terms of compactness, is very interesting. But I think the most interesting part of it is that instead of having to curve material like this, you know, as it is generally done in refractive optics, now you could think about fabricating optical component using wafer level fabrication. So you can really make flat optical component using CMOS fabrication facilities. And with this approach, I will not enter in the detail, but you can control the phase, the amplitude, and the polarization of light directly at interface. I show you here one picture I stole from Federico's website, where they show, you know, the realization of a volumetric, macroscopic size device that are like tens of centimeters in diameter, to show that this technology now is moving to realistic device. Here is one example of the first example of wafer scale fabrication of meta lenses. And I show you here some of the results in our lab using a 300 millimeter fabrication of metasurface glass on silicon on glass wafer that eventually is composed of many of those meta lenses. So the way we design metasurface, it works by essentially engineering the light interaction with nanostructures, as I mentioned, that are disposed at interface, and we rely on a variety of physical mechanism to control the actual transmitted properties of light. In fact, we have identified 3 main mechanisms that are useful for that can be useful for the design of metasurface. The first one is called the resonant interaction, resonant scattering of light, where light resonantly coupled with the internal modes of the nanophotonic system, could be plasmonic resonators or dielectric resonators. The second mechanism is called the Pancharatman-Berry phase. This is a bit more not intuitive. It works by relying on polarization conversion, where you design nanostructures that are operating in the polarization domain, so that essentially behave as a birefringent type of material here, these nanostructures. And they can convert polarization from, let's say, circular polarization right to circular polarization left. And then by rotating this nanostructure, you are essentially doing this polarization conversion, but following different trajectories of conversion in the Poincaré sphere. And this different trajectory provide on the converted polarization a phase which is proportional to the rotation angle. In fact, twice the rotation angle. So by rotating this half-wave plate nanostructure, you can engineer the converted phase with a relatively high efficiency. And the third method, it's a bit more conventional, is essentially making nanopillar structures with varying diameters so as to operate as nano waveguide, if you want. And by changing the diameters of those nano waveguide, you change the actual mode index. And so you increase the refractive index of the waveguide by simply increasing the diameters. And you end up, therefore, for a fixed height with a gradient of phase response at the output. So these are the 3 techniques which we were convinced about having and understood for the design of metasurface. We have here a review paper we wrote with Federico back in 2017. My group very recently realized that this mechanism of resonance scattering is not perfectly well understood. And what I propose here in this discussion today is to replace these problematics here with what we call singular scattering, and try to study how the topological phase singularities, and I will explain what it is, are used to design metasurfaces and introduce essentially phase modulation. Singular optics, singularities in photonics exists since a long time. The first paper, in fact, was proposed by this guy, Pierre Coulet, who was a professor at the University Côte d'Azur here in my university, where he introduced for the first time the concept of optical vortices, which are essentially phase singularity, where the phase is rotating over 0 to 2 pi with an azimuthal phase distribution. And you see, as you get closer and closer to the center, the phase is evolving so fast that is not possible to do. It's at the center, it's becoming essentially singular. And that's what we call phase singularity. And this technology, since then, evolved quite a lot, up to today, where we are really able to manipulate and control these optical vortices. And what I show you today is that optical vortices and the fact that we have phase circulation with a region of undefined amplitude exactly at the center are essentially the key to understand the response of nanophotonic system and the diffusion of light in general. Why do we have singularities in photonics, and why is it important? To understand that, I would like to mention the fact that metasurface essentially are systems that are interacting with the environment. In fact, any optical devices are interacting with the environment. You are sending the line in, and you are using the device to essentially project light outside or focus light, right? So you have interaction. So you are not operating in a system which conserve light inside, right? So you don't have energy conservation. The system, nanophotonic system, but optical system in general, are called non-emission because they interact with its environment with transmission or even absorption loss. So instead of having real eigenfrequencies, the presence of losses here is such that the light inside the resonator decays in time. And so the only way you can characterize the resonance of this system is by considering complex eigenfrequency, where the imaginary part describes the decays in time, right? And that brings to the concept of what people call the quasi-normal modes. that eventually describe the non-hermicity of those resonances. And this non-hermicity here, it's actually very interesting, and because it's not only the fact that all optical systems are generally non-Hermitian, is because non-hermicity brings new type of physics. For example, you could have what we called parametric singularities, where multiple eigenstate here, for example, at this exceptional point here, become coalescent. The Hilbert space that represent the system is not anymore complete, and that brings an ensemble of anomalous effects, including spontaneous symmetry breaking, directivity, chiral state transfer, divergent resonance shift. I will show you some of these examples here in nanophotonic system. But to understand a little bit more in detail what I'm talking about, what I'm doing here, I'm taking one of the most simple nanophotonic system that you can imagine, which is a Fabry-Perot. And what we are going to do here, we are going to send in light in a Fabry-Perot, which is a slab of material between two mirrors here that are represented with reflection coefficient R1 and R2. And we shine light into this device, and we look at the reflection coefficient, for example. It comes from the interference between the first reflected light and the secondary waves that are interacting with the actual resonant modes of this Fabry-Perot, right? So you have a sum of the secondary waves here, and so you have R0 plus this sum, and you can eventually simplify this expression, and it comes at a very simple expression here for the reflection coefficient, where you have here numerators that takes R1 and R2 reflection coefficient plus a phase term multiplied by a first phase term, and the denominator, which is written by 1 plus R1 R2 times this phase term here. I'm introducing this expression because it's become very extremely useful to understand the concept of singularities that I have been mentioning. You see that this delta here is the actual round trip of the actual phase inside the resonator here. So it's a function of the actual frequency omega. So we could sort out all the frequencies for which the numerators is equal to 0, and all the frequencies for which the denominator is equal to 0. So I do R1 plus R2 delta here equal to 0. Then you immediately come up with this expression where, taking the log here, you have essentially this round trip phase and the logarithm of R1 and R2. And interestingly, you see, and you do that for the numerators and you do that for the denominators, so you have these two expressions of the 0 frequency. And interesting, you see that when R1 and R2 are not necessarily equal to unity, so when the system is essentially interacting with the environment, then you see that now these zeros and this, what I call pole here, are becoming complex quantities, right? So you have a complex expression for the 0 and poles. And it can be shown, you know, that every complex coefficient here can be written. It's called the Weierstrass formulation here in terms of a product of 0 and pole singularity. So from this basic analysis here, you immediately see that when the system is interacting with the environment, you have to study this problem in the complex frequency plane. So, but generally, when we actually send light into a device, we are sending real frequency, and we are studying, for example, and I show you here the reflection coefficient, amplitude, and phase by sending a plane wave here, measuring the actual reflection coefficient as a function of the frequency. And then what I'm going to do here in this plot, in this map, I show you the evolution of the amplitude and phase of this reflection coefficient for R1 fixed equal to 0.5, and I change gradually this R2 coefficient. And then I see as I increase the R2 coefficient and I look at the amplitude of the reflection, at some point I see here, you know, appearance of a 0 of reflection. And associated to this 0, when I look at the phase here, I start to observe, you know, appearance of this phase singularity that I mentioned before. It appears in the parameter space simply by changing the reflection coefficient R2. And you see, when R2 here is equal to unity, so when the light is fully reflected, then you have a unity reflection amplitude for all of the spectral range of interest. And it looks like there is no resonance, right? But if you look at the phase here, you see that now you have a phase jump that covers essentially 2 pi. This is what people called in photonics Gire-Tournois resonator. You see that I come back to the case here when I have this Fabry-Perot resonator, when R2 is equal to 0.5 at the position where I see this singularity here, is when R1 and R2 are equal. You know, when R1 and R2 are equal, it's like having a system which is Z inversion symmetric with respect to the optical axis, can be inverted, and I still have the exact same system. So symmetries here play a role, and the position of this appearance in the parameter space of these singularities are essentially related to the symmetry of the problem. I can discuss that later on if you are interested. But you see, these measurements here are done with a real frequency excitation. We haven't studied these complex frequencies here. So what I would like to do is, instead of exciting the system with steady state response, which is omega real, I would like to start interrogating this problem here, this Fabry-Perot or this meta surface, with time varying excitation, so that we can provide, if you want, into the excitation frequency a complex part. We can send exponentially increasing, which provide the positive imaginary part for the excitation source, or we can send exponentially decaying source, and that provide essentially virtual gain or loss into the system. And that can be referred to this paper here from Andrea Lu, where they have studied excitation of these complex quantities. So why are we doing this? You know, because generally, as I say, we send light in, we measure the reflection coefficient or the transmission coefficient of a system by sending only real omega frequency. And we could observe sometime some resonance, if you want to. People call that resonances here, where it looks like some sort of a spectral response on the transmission and reflection coefficient. And if you look at the phase, you have some phase variation. Now, what we are going to do, we are going to send not only a real omega frequency here, but we are going to send a complex omega, which means I send a real frequency and also an imaginary part, which correspond to an exponentially amplifying or exponentially decaying source, to observe the response and probe the response of the system in the complex frequency plane. And then what we do, we take the log of this transmitted reflection coefficient at every single point with complex frequency excitation, and we extract the amplitude and the actual phase by taking the log of this transmission coefficient. And you see that the log will directly provide the actual phase of the reflection coefficient. And then what is interesting is that when you do that, you start observing the quantity that I've been discussing before, which is the presence in this log of divergent quantities here, these zeros and this pole here that are essentially here like infinite singularities of the log, and zeros here that are the zero of the log of the transmission of zeros, you see. Now, if you look at the phase associated to this transmission coefficient, you see at the position where you have these singularities, these zero and poles here, then you see in the phase diagram appears, you know, this spectral optical singularities that I mentioned before, where you start to have, you see, a circulation of phases that start exactly at the position of those zero and poles. And you see, like those zero and poles, you know, if you look at the phase, you know, it's very striking. They are connected singularities with clockwise rotating phase for the pole and counterclockwise rotating phase circulation for the zeros. And these are very important, you know, and I call the zeros the zero and the pole the divergence of this law. Why is it important? Because you see, like if you do a normal plane wave excitation, sometimes you see a feature here that goes to zero in your transmission coefficient and you don't know where it comes. It comes simply because you bring the zero of your transmission complex omegas at the real frequency axis, and so you can observe it, right? But it's not always the case. Suppose that, for example, the zeros are below the real frequency axis, you would not see any relevant spectral response here at real frequency. You have a phase modulation that is very small. You can tune the parameter to bring the zeros here. You will have a zero in the coefficient, and you start to have a divergence, like a discontinuity here in your phase plot. And if you keep changing the parameters, you could be in the situation where zero and poles are essentially separated from the real axis. And this is very interesting, because if you are in the regime for which they are separated, you see now the signal with real frequency excitation, if you send essentially your plane wave varying the frequencies and look at the phase here as it is done here, you see you have now like a discontinuity here, which when you sum up here, you get 2 pi phase, right? And this is very important because if you want to make design of photonic system for wavefront engineering, you have to be able to engineer the phase over 0 to 2 pi, you know. So generally, if you rely on a resonance scattering, you want to find conditions for which zero and poles are separated. And the reason why you have 2 pi phase essentially come from the complex analysis. They say that basically the integral of the phase on the real axis here is equal to the complex plane circulation. And if you have singularities in the loop here, that in which you do your complex plane, the residue theorem here tell you that you have essentially a phase circulation that range between 0 to 2 pi, essentially 2 pi times the number of singularity inside the loop. This is what we discussed very recently in this paper. I'll give you a bit more of in-depth flavor of what it brings into the. But you already see here that if you want to do meta-surface or design of nanophotonic system using resonant phase, you need to be in the regime for which your zero associated to the coefficient in which you are going to modulate your wavefront has to have a positive imaginary part. So for the design of meta-surface, what you have to do is to search in the parameter space singularities, zeros, that will help you to reach a resonant condition for 2 pi phase. And this metasurface, you know, it's a very interesting technology because it provides, if you want, a huge number of knobs, you know, to test and validate this topological photonic concept. You can play with the shape, the geometries, you can play with the chirality, the orientation of the structure, and it's very convenient. So what I'm going to do now, I'm going to guide you a little bit more in the description of metasurface. So we have these nano-resonating building blocks that are eventually taking signal in via a various type of incoming channels, and that are reflected or transmitted light depending on the channel you are considering. So you can essentially describe a metasurface via this S matrix here that connect input and output channels. And so what I'm going to do here, I'm going to use the trick that has been proposed by Professor Shanwil Fan in this Josabi paper here, where you describe one of these resonant metasurface or resonant nanophotonic system by considering the output channel are connected to the input channel via non-resonant background that interfere with the actual resonantly scattered light from each of those resonances of this nanophotonic system. And each of these resonances are described via a simple equation that describes the scattering amplitude of the actual field by relying on the interaction of the modes with the resonant frequency and their decay rate, this D1 coefficient that describes the outgoing signal, plus the function of the actual incoupling field, you know. So then I'm going to do a little bit of a trick here. We assume time reversal symmetry such that the incoupling and outcoupling by time reversal symmetry are equal, so that it simplifies essentially this expression. Kappa is equal to D here, and you end up by getting a very simple expression with harmonic oscillation of the modes, and you can express this amplitude here, inject into this expression, and you can come up with a very simple expression for the scattering matrix, where you have here a resonant interaction of the light with each of the resonant modes that are described by this Hamiltonian response here. So now I'm going to do a little bit more of a trick here. I'm going just to decompose the input and output modes here by using this D1 and D2 separation, where D1 describe all of the modes on the upper part and D2 all of the modes on the lower part. So if you come with direct excitation here, the upper part will define the reflection and the lower part will define the actual transmission. And you have the time reverse version of this, so that you can eventually rewrite this S matrix into 4 sub-blocks. And each of the blocks will correspond to the actual reflection transmission, the time reversed transmission, and the time reverse reflection. This is very handy because with this expression now, we have an expression for the scattering matrix interacting like light interaction with each of the resonant modes. And we have in each of the subgroup of this matrix, the reflection and the transmission coefficient that are becoming very useful for studying the response of this metasurface in the presence of resonant photonic modes. So we can, for example, look at the reflection coefficient and do exactly what we did with the Fabry-Perot, which is to look for the reflection zeros. So all the reflection zeros, meaning that all the light is reflected, transmitted, sorry, nothing is reflected, or all the light is actually absorbed so that there is no reflection. So I take this expression for these reflection zeros that we calculated together. I do a little bit of math here just to write it in the format that we like, which is the numerator and denominators, where we can study the zeros of this determinant and the pole. So you have now, if you want, with this simple expression, an expression for the zeros and the pole of our meta surface response. So if you haven't understood everything in the detail about this decomposition and this what we call time coupled analysis here, the couple mode analysis, what matters is that we were able to express the zero and pole of a resonant system in a very simple form, where we have here the resonant frequency and the actual coupling terms to the environment. And now we can study, let's suppose, only one resonance and one input channel and no absorption. So we have only one mode, and we have light coming in. Light can be reflected or light can be resonantly transmitted. And so we can write the expression for the reflection zeros and the reflection poles here, where it comes with a very simple expression. And you see now the zeros appears with a plus and minus terms here, while for the pole, the imaginary part is always negative. So imaginary part of the poles is always negative. It comes from causality consideration. But for the zeros, you know, you could find regime for which D1 and D2 are equal, which is when the gamma 1 and gamma 2, where those two quantities here are equal, when the system radiates forward and backward as much light, then if you want, when the system is, and we come back to what we said before, the inversion symmetric, you see that the imaginary part vanish and you have only real frequency for the zeros, right? So this becomes very handy, because with this expression, depending on gamma 1, gamma 2, we can find regime what we call undercoupled regime. The critical coupling regime, which is when the imaginary part is equal to 0, when the system is the inversion symmetric or parity symmetric, if you want, from the actual topology, topological photonic language, or if it's imaginary part positive, you can find the overcoupling regime, which is the regime in which we are interested for the design of meta surface. So I'm taking here another example here. It's a metal dielectric metal structure where you have back reflecting light metal here that forbid any transmission. This gamma 2 is equal to 0, and we can add, if you want, some absorption loss that comes as an imaginary part here. And you see, you can again study the same problem. The zeros can become eventually real when the scattering gain equate the actual absorption losses. And I show you here the same type of simulation, where I look only at real frequency excitation. I look at the reflection coefficient to measure this S11 coefficient here on the metal dielectric metal structure, changing the real frequency excitation and the geometry, essentially as what we did with the Fabry-Perot previously, and you see appearance here of a 0. And at the position of this 0 in the parameter space, again, you see appearance of a phase circulation. So you see that when the system becomes essentially with an imaginary part of the 0 equal to 0, you are able to observe in the real frequency excitation the 0 appearance here. So you have, if you want, with this expression, able to identify the region for which the system is undercoupled, for which the actual 0 of reflection coefficient is below the real axis. When it comes exactly at the critical coupling condition where the 0 becomes real axis, and changing the parameters again, you find the overcoupling regime for which you do have the 2-pi phase modulation of interest for the design of meta surface. This is essentially what I've been observed in various papers where people have been designing this kind of metal insulator meta surface, but never explaining that by looking at the position of those 0 topological phase singularities that are essentially the key quantities to really describe the physics. You see, when you pass the critical coupling condition, right, when you pass beyond this blue curve, then you start to see a 2-pi phase variation that comes from the under to overcoupled regime. This has been used also by one of my good friend Talel and Bogen here, where they have been using again this metal insulator metals, where you see the zeros here of the reflection coefficient, and you start to see again the phase here, and they use it for wavefront engineering. In fact, it's used always, all the time, in all design of meta surface. You know, in order to get 2-pi phase modulation, here it's an example from this Samsung paper here where they show that they were able, by applying 2 different type of voltage into this metal insulator metal structure, they were able to engineer reflection phase from 0 to 2 pi. And that works simply because, again, you see in the parameter space, they were able to encircle zeros. So we understand the physics of a reflective metasurface. I would like to show you what happened in transmission. So I'm considering this time not the reflection zeros, but the transmission. So all the light is not transmitted, it's reflected. And I would like to consider one of these systems where you don't have any absorption. So because you don't have absorption coming from this channel and reflected here, and coming from the lower one and reflected in the upper one, is essentially the same by time reversal symmetry. Right, so because of time reversal symmetry, the transmission zeros have to be essentially complex conjugated to or real, right? So they have to be complex conjugated to each other, or they have to be real by symmetry consideration, because the system is time reversal symmetric and is the same if you reverse the channel, so it's the same zeros. And then I did that just to introduce what people call Huygens metasurface. You will see that essentially Huygens metasurface essentially is described because of this like a zero transmission zeros. So I took one of these geometries here that is used in literature to show Huygens behavior. So it's a dielectric array of nanoparticles embedded in homogeneous material. And by changing the geometry here, people were able to show that the transmission coefficient eventually shows 2 transmission lines here, changes as a function of parameters and eventually converge. And then there is some sort of a unity transmission here that comes when the 2 resonance seems to be overlapped. And then you have, again, these 2 transmission zeros on the other side. So if you observe the phase here, sorry, there is a noise here in my office. I will have to stop it. Just 1 second, I come back. Désolé, est-ce que vous pouvez arrêter juste quelques minutes? Parce que là, merci. Okay, sorry about that. You know, like they're making some homework. Okay, so now what we're going to do, we are going to show, you know, that those zeros here are essentially what govern or control, if you want, the response of the system. So I show you here this phase plot here for a geometry which is far away from the Huygens regime. You see 2 zeros here. You see 2 transmission zeros. And if you look at the complex plot, the phase of this complex excitation plot, you see that you have 1 zero here that is associated to 1 resonance and another 0 here associated to a second resonance. They are very separated apart, and they are on the real axis. I remind you, because it's no loss, they are supposed to be on the real axis by a symmetry consideration. And now I plot what is happening here, exactly in the middle of this Huygens regime. And then you see that now one of the 0 move up and the second move down, and the value of those 2 zeros essentially are complex conjugated with opposite imaginary part. And I will explain what happened. You know, it's actually related to what people called spontaneous time symmetry breaking. What we are doing here, we are following in this line here the real frequency of these zeros and the imaginary part of these zeros. You see that the real frequency of zeros eventually converge to this point. They remain the same and then they split again. And if you look at the imaginary part, the imaginary was equal to 0, the 0 were on the real axis, up to the point where we enter into this regime where the imaginary part and the real part are superposed. It's called the exceptional point, a topological phase singularity with phase that is essentially varying from 0 to 4 pi, because you get twice the 2 0 collide if you want, and then they move complex conjugated away and they recollide past this regime. You know? And for that, I need to show you here this video. I think it will very well help understanding what's going on here. I show again the phase, imaginary and real part of the phase plot as a function of geometry, where we start with a height of 120 nanometers, and we show this complex plane where you have the zeros that are on real axis, the electric dipole, magnetic dipole. And you see when you start changing the parameters, increasing the height, the 2 0 collide, they move complex conjugated apart in the complex frequency plane. Then this 0 pass to the other side, this pole, sorry, they pass to the other side, and then the 0 merge again. This is fascinating. You know, what is happening here is a spontaneous symmetry breaking that is due to the fact that you see the red structure here, the red cross, which is the electric dipole, move as the parameters much faster than the actual magnetic dipole because it's more confined, you know, so it's more sensitive to geometry, but he moves so fast that he wants to change, go to the other side, but he cannot. Otherwise, you have to cross, you know, this line that connects zero and pole that we call the branch cut in topological photonics. And you cannot, like, it's a topologic problem. For this to happen, the zero has to move sufficiently far away to leave some room, you see, to leave the room for the actual pole to pass to the other side and then collide again. Very fascinating problem. This is what I can call, you know, it's been discussed for real frequency, what people call avoided crossing. This is essentially an avoided crossing of complex singularity pairs of zero and pole. You know, it's an avoided crossing that comes by the essentially spontaneous time symmetry breaking. And this is what is behind the Huygens metasurface. Metasurface has topological origin, very fascinating. Anyway, so now that we understand the design of nanophotonics for engineering the phase, because you see here, when you are in this regime here, the zero and the pole of one resonance are separated across the real axis. So if you do circulation of phase here on the accumulation of phase along the real axis, you get 2 pi. You know, this is like essentially what is shown here. You get a 2 pi, but with unity transmission efficiency. Okay, so we have understand that we need zeros. Can we create other zeros in the parameter space for designing metasurface? Yes, one way to do it is to use degeneracy. Degeneracy is like one of these singular points that I mentioned before. How can we do it? I'm going to take an example here of the Jones matrix. Jones matrix is a matrix that connects input polarization state with output polarization via a matrix that contains A, B, C, D complex quantities, because we are talking about amplitude and phase to describe the actual transmitted or reflected polarization states. And these are complex coefficients. I'm going to do an energy shift as they do it. It's called a gauge transformation, but it's a very simple expression that enables us to rewrite the G matrix in a degraded form where we have only 3 independent coefficients, A, B, minus A and C. These are complex quantities, and we can immediately calculate the eigenvalues of this matrix. We calculate the determinant of a 2 by 2 matrix, A minus U, B minus A minus mu, and you end up by getting the determinant, which is written as the square root of plus or minus square root of A square plus BC. So you see that when what is inside here, what is inside here is equal to actual zeros here, you have degeneracy. The 2 eigenvalues are equal, you know, and you have 2 possible solutions, and associated to these 2 possible solutions, you have 2 possible degenerated eigenstate that are written like this. Summarizing the problem, we have Jones matrix to calculate eigenvalues, and at the degeneracy condition where eigenvalues are the same, you have eigenstate that are written like this. I'm going to simplify here. I'm going to consider that B and C are equal. That is related to some sort of a reciprocity here. Then you see that the eigenpolarization here, degenerate eigenpolarization state are become circularly polarized state. Why is it interesting? Suppose that we are operating with one of these degenerate circular polarization at the degeneracy condition. You see that when I send left polarization, because of degeneracy, I get only left, for example, transmitted or reflected polarization, which means that if I send now, there is no polarization conversion, right? So you are creating in the polarization conversion a zeros. But if you send, which is characterized by this polarization conversion 0, but if you send right, because it's not eigenstate, you can have both state here. So we designed one of these nanostructure here that provide a 0 of polarization conversion on the plus to minus channels here by changing the geometry of this structure, and you see that you have a 0. And again, associated to 0, you know the drill now, you start to have a phase singularities that eventually wrap around 0 to 2 pi in the parameter space, right? You have this 2 pi phase circulation. If you do minus to plus now, if you do the opposite polarization from right to left, because you are not degenerated polarization eigenstate, you are not expecting anything, and you are not expecting to have any phase circulation. Which means that if you pick up phase element here for this plus to minus conversion, you will have 2 pi phase, while here you have essentially flat response. So we fabricate one of these structure here, make one of these phase gradient metasurface, And you see that if you look for the plus to minus polarization conversion with this phase gradient metasurface here, you see appearance of a beam that is deflected at the period defined by the phase gradient period of the structure. While if you look for the other polarization conversion, you are essentially reflecting normally. We made the experiment, observe this with a very strong asymmetry between the plus minus and the minus to plus conversion channels. You can use it for wavefront engineering, for example, if you send plus on a metasurface which is designed to produce, for example, hologram, you see these holographic oscillators. But if you reverse now the polarization and the conversion, you essentially see nothing because it's not supposed to work for it. I don't know how far I am with time, but I'm going just to very quickly introduce also the possibilities of adding to this topological phase or like a polarization zero, conversion polarization zero phase rotation to this structure, which eventually brings what I mentioned at the beginning, the topological phase, and you can combine those two like phases so as to decouple. I'm going to skip that, just show you the results. So as to decouple the two plus to minus and minus to plus channels, where you are able to engineer the two different circularly polarized state of polarization very independently one from the other to project light, for example, at two different angles, or for example here to project images, holograms of a different shape that are very different one from the other at two different angles as well. So I will briefly mention here this work on LiDAR here to conclude this presentation from, let's say, an applicative point of view, where we are essentially using this design metasurface structure and integrated them into system. And the system I'm going to talk about is a LiDAR, which is used for 3D mapping of the environment. What we did here, we cascaded one of these acousto-optic deflector that is doing a very small scanning angle, but very high frequency, with a metasurface here that is designed such that depending on the impact point of the metasurface, on the laser, sorry, on the metasurface, we will pick up a different phase response. For example, if I send the beam without any deflection exactly in the center, so if I shine the light exactly in the center of my metasurface here, because there is no phase gradient here, the light will essentially go straight. While if I start essentially deflecting the beam with the acousto-optic deflectors, I will start picking up a phase gradient, and I will be able to expand and change the deflected angle up to 100 and 150 degrees field of view. So this is the top view. The laser is sending to the acousto-optic. You have 2 degrees, and then at the output, you end up by getting a very large field of view. And by pulsing the beam here, we can eventually create a scanning beam that scan the scene in a 3D, 2D angle, and by measuring the time of flight, we can measure the time it takes from light to come back from this scene. This is a scene with a few of my students wearing reflective clothes, and then I scan the scene and measure in the time of flight, the actual round trip time of the light at every single point here. And you see that it appears now those people here, so we see their images, but also we encode in the time of flight the actual ranging distance. And you see here the color coded shows this guy is like deeper, this one is middle distance, and this one is closer, about 1 meter away. Here is a video that shows the system running in the real time, intensity on the light on the left, which is reflected intensity, and time of flight encoded on the right, where you see that people here are exchanging a ball here at a very high speed, where they can, you see the people moving back and forth from the screen that essentially shows the 3D encoding of the actual time of flight information. So I'm finishing this presentation by saying that we have been able to develop now the system working at 905. We can have a 905 system for LiDAR that use one of these metasurface here that are fabricated using deep UV lithography from ST Microelectronics. And I show you here, I'm just going to switch off here the sound because it's very noisy otherwise here. Yes, and I'm going to show you the actual videos at 905, where you have, this is normal camera, this is the reflected intensity, and this is the actual time of flight, where you see again people that are able to exchange ball. You see them moving back and forth. you see a very crisp reflected intensity and color coded. You have the possibilities of observing the actual depth position of those people here. That shows essentially that we are able now to obtain high resolution LiDAR images with a very high frame rate imaging up to a kilohertz frame rate. So I don't know how I am with time. I'm sure that I'm getting close to the end here. So I'm going to conclude by saying that topological nanophotonics that I introduced during the first part of this presentation, I believe open new and exciting directions for research. And I show you, that this topological response of nanophotonic system provide fundamental understanding of the scattering mechanisms that are generally used for the design of metasurface. I show you that the crossing of the branch cut between the zero end poles essentially provide the 2 pi phase accumulation needed for metasurface design. I give also a formal explanation of the metasurface, Huygens metasurfaces, and I show you that essentially the zeros play an important role and that phase singularity has to be considered to really understand the response of photonic system. I show you that we can create new zeros and encircle them for wavefront engineering. These are the results here of this very recent science paper. And I came to the end to a demonstration with system integration where I show you essentially the use of metasurface for high frame rate LiDAR images. I just would like to conclude, because we have, I'm moving to the Colorado School of Mines starting in July in the beautiful golden city of Colorado, close to Boulder. And I'm looking for motivated and creative PhD students. So if you hear about any PhD student interested in working in nanophotonics and using this metasurface for system integration, I will be very happy to discuss with them. So please don't hesitate to share this email to any possible interested student. And with that, I would like to thank you for your listening, and I'm very happy if there is any question. I will be happy to answer. Thank you very much.
Thank you so much, Dr. Genevieve, for the insightful presentation. So I can see that we have a question in the Q&A box. Maybe you can answer it later after Dr. Pabisi's presentation. Yeah. Dr. Lorenzo Pabisi, I'll pass the time to you now. Maybe Dr. Genevieve can stop sharing.
Sure.
Thank you.
Okay, so thank you very much for the opportunity to talk. Okay, that's condividing. Okay, so thank you very much for the opportunity to introduce what we are doing in the field of neuromorphic photonics. So I'm coming from University of Trento in Italy, and I'm leading a group that is called the Nanoscience Laboratory, and we are working essentially on two different topics. One is advanced nanomaterials for energy, environment, and life. And the second topic is about silicon photonics, where we are working on quantum photonics, non-Hermitian photonics in a very similar way on what Patrice was saying before, even though we are working on integrated photonics and not on flat surfaces. And then we are also working on neuromorphic photonics. So if you are interested to know about what we are doing, so either you can have a look to the 2022 highlights of the lab, or if you are interested to get to know what is my view on the evolution of silicon photonics in these last 30 years, so you can read this review paper that I wrote a couple of years ago. But let me go back to the main topic of today's talks, that is about neuromorphic silicon photonics. And our idea, so our vision, is to try to build up an hybrid artificial biological network where we make a photonic integrated circuit to interact with biological culture. And the reason why we are aiming to work and try to achieve this vision is shortly introduced in this small video here. I hope to be able to run the video. Why is not starting? Anyway, so I don't know why the video is not working. So let me try to let the video run. Okay, so you can have a view of the video in this YouTube link. So essentially the idea why we want to make this hybrid artificial biological network is because we want to make both worlds to compute together. And so let me start with the first ingredient in this vision, that is the development of an artificial network that is based on photonic integrated circuit. So the platform that we are using is silicon photonics. And by using silicon photonics, what essentially we aim to do is that to have a full pack of different optical component squeezed down in a very small integrated photonic circuit. And the reason why we aim to do that is because in this way we can make much more efficient devices, because we no longer have issue about alignment, instability, noise, coupling loss between the different macroscopic devices. On the other hand, the possibility to have a photonic integrated circuit led us to have a smaller dimension, lower cost, and especially the possibility to integrate on the very same chip both electronics, meaning computing, as well as optics, meaning communication. In this way, so we can have and promote a widespread diffusion of the integrated photonic circuit. So the kind of circuit that we want to develop are inspired, and this is the reason why it's called neuromorphic photonics, are inspired on how the brain works. And the reason why we want to get this neuromorphic photonic reality is because the brain, and we get inspiration by the brain, because the brain is really a model for power efficiency as well as performance. Indeed, so the brain is always working even when we are sleeping, as well as we are able to fit, the nature was able to fit in a very small form factor, billions of different computational units. As you well know, so this field of brain-inspired computing is the field that is behind the success of artificial intelligence, where we have observed in this last year a boom of the performance of the artificial intelligence model. And this increasing of performance is also followed by an increase of the number of the neurons that are contained in a single model, that nowadays are in the order of a few thousand billions, as well as the problem associated to the power consumption that are needed in order to run those artificial intelligence models. Just to give you some numbers, so the power that was consumed to train ChatGPT is of the order of 1 gigawatt hours. And to quote, to simulate, to place in perspective this number, just consider the human brain. So human brains typically to think, so we consume something in the order of 20 watt. In order to train humans, let's say that we take 20 years. And so now if we compute the power that is consumed to train a human brain, so we end up with a number that is only 3 megawatt hours. So that means that in order to train an artificial intelligence model, so we consume a power that is equivalent to educate more than 500 people. And so the idea is to use photonics in order to match this power issue. And indeed, so several different integration schemes for different concept of photonics that have been proposed in the past. And what is the reason why we want to use photonics in order to implement a artificial intelligence model? So photonics is a platform. So one of the reasons is because light is fast. The second reason is because it's power efficient. And the third reason is because photonics naturally use a parallel scheme. Let me concentrate on the speed of light. So typically, we already saw that in order to learn, a human being takes in the order of 20 years. But now, if we compare the typical switching times of a biological neuron, that is of the order of the millisecond, with a typical switching time of photonic neurons, which is in the order of the picosecond. So we see that we have 9 orders of magnitude between those two time scales. So that means that if we are able to make an artificial optical brains, so the learning will take only half a second instead of 20 years. So this is the motivation of using photonics for neuromorphic application. But in order to show you an example of a photonic integrated circuit that implement neural networks, I want to go back to the basics. So this is a scheme of one of the computational unit that we have in our brain that is a neuron. And so this neuron is connected to nearby neurons. And what happens in a neuron is that the information are collected coming from the nearby neurons and are processed in the soma. And if the amount of information that the neuron is receiving is larger than a threshold, so then a spike is generated by the neuron and sent to the nearby neurons. And so this concept is at the base of a model, an artificial intelligence model that is called a perceptron, where data are input through, are weighted and then input in the body of the neurons, and the weight sum of the input data is non-linearly transformed in an output quantities. And depending on the target output, so the neurons during the learning phase has their weight that are changed so that the output match the requirement. And so this is the basic unit for the neural network. And so now what we want to do is that we want to make an optical neuron. So where we have inputs data, we have to perform a weighted sum, and then we have to non-linearly transform, non-linearly output the result of this weighted sum to the next neurons. And so in optics, we can do the activation, so the nonlinear transformation very simply. So we take the electric field that is input into the photonic circuit, and then by simply measuring the intensity, so we square the electric field. And so that means that now, so we have this nonlinear activation function that allows us to achieve the desired output function. And so a critical ingredient here is the way we do the weighted sum. And so the idea is simply to use optical interference. And so by controlling the phase of the light that is reaching the interference here, that is interfering in these points, so we can change the results of the sun. And so in order to control the phase, so we simply use a very simple device that is a thermal phase shifter. And so this thermal phase shifter is based on a metal wire that is grown on top of a silicon waveguide. And then by letting a current flow through the metal wires, so we heat up the metal wire due to the Joule effect. So it is moving from the wire to the silicon waveguide. And then, since the temperature dependence of the refractive index, so we can control the refractive index of the silicon waveguide. And now, if we let the light beam and electric field pass through the region which we heat up, so we can control by controlling the temperature, meaning by controlling the current that is flowing the metal wire, so we can control the phase shift that is imprinted on the light field that is moving below the thermal phase shifter. And so this is the way which we use in order to control the weight in the sun. And then we built up a very simple device that is a complex, time-delayed complex perceptron that is used in order to implement a neural network that is performing quite well, as I will show you. So the device is given in this sketch here, so where you have an optical fiber and the light signal is entering through a grating coupler and then is split in 4 different lanes, in 4 different channels. On these different channels, so we insert delay lines, and so what we get is that a delay representation of the input light. And then the reason why we use these delay lines is simply because we want to make interact in the sum the state of the input at the present time with the state of the input at past time. And so by controlling the length of the waveguide, so we can control the timing of the arrival of the input signal at the point where the interference occurs. And so in this way, so we make to interact the present bit with the bit in the past, with the bit in the farther past. And then this interaction, this sum, is achieved by letting this delayed representation of the input through the phase shifter, whereby controlling the current, we can control the additional phase that the light field is experienced. And then these weighted and time delayed representation of the input are made to interact, interfere in this point. And therefore, what we get in the output waveguide is a weighted sum where each single weight is controlled by the injected current in the chip, so it's a weighted sum of delayed version of the input bit stream. And then in the detection, we get the nonlinear square function that allows us to achieve the desired output. So this is the device, and the device is integrated in a very small photonic chip circuit. We have all the line here, the metal wire that is used to inject the current into the neural network. And then I will show you one application of this very simple device that is very well performing. And so the application is about the propagation related distortion that an optical signal suffers due to chromatic dispersion when it's traveling along a fiber of a few kilometers length. And so what happens because of the chromatic dispersion of the optical fibers, so we get a pulse broadening. And so the pulse broadening is such that we have intersymbol interference, which makes that now we lose information whether the bits that are coming out that have been transmitted by the fibers, so we lose the information about the fact whether the bits are 1 or 0. And so our goal is to use a neural network in order to recover the input information, meaning in order to mitigate it for the chromatic dispersion. So the problem is the fact that when we let the light, an optical signal going through 100 kilometers of fibers, so we get this intersymbol interference, which makes that the fact that if we look at the histogram of the ones and of the zeros, we have that the two histograms overlap. And this means that in this overlapping region, we lose information whether the bit is 1 or 0. And so what we want to do is that we want to teach our network in order to separate again this histogram, meaning that we want to clearly separate the ones from the zeros. And so we run the network, so we teach the network to do this recovering of the chromatic dispersion, and these are results. So the data rate was 10 gigabit per second, so the fiber length was 125 kilometer long, and this is the A diagram for the input light. These are the histograms of zeros and 1 from the input light. And then what you see is the action of the chromatic dispersion that after the signal has propagated 125 kilometers in an optical fibers, so we have completely lost the information. So the high in the A diagram has been closed. And therefore, so now we have that the two histograms of the zeros and 1 are overlapped. And then after training the neural networks, so this is the output. And so what you see is that the IA diagram is open again, meaning that now we are able to distinguish the 1 from the 0. And so in this way, so we can get a bit error rate, so the number of errors in the bits that has been received by the detector, we can have a bit error rate that is similar to the one or equal to the one that was present before transmitting the light signal through the fiber. And so here are the results for 100 kilometer fiber length at 10 gigabit per second. So this is the bit error rate for the transmitted light in the optical fiber, so the red points, while the blue one are the bit error rate after the action of the neural network. And what you see is that the bit error rate is overlapping the bit error rates that we are measuring without the optical fibers. So that means that the neural network is able to recover completely the initial information. And this happened at 10 gigabit per second or at 40 gigabit per second, or even if you are using a more complicated transmission protocol like PAN4. So in this transmission protocol, so you have 4 different levels instead of 1 and 0. So you have 4 different levels. So this is the actual recording measurements after 100 kilometers of fibers. So you see that you lose completely information whether the bit is 1, is 0.75, 0.25 or 0. So you completely lose the information of the bits, while after the fiber and the neural network, so you recover the clear separation between the different bits. And so this means that this very simple neural network is able to perform a very complicated function that is very important for optical communications. And so we also have elaborated other different neuromorphic circuits that are able to perform and achieve other different functionalities. And if you are interested in a review about what we did, so you have simply to look at this work here. So let me go back to our vision. So the vision is to have the photonic integrated circuit in order to make an artificial network. On the other side, we want also to capture a biological culture in order to make a biological network and using light to stimulate and to make the neurons perform as we desire. And so in this case, the platform is a living culture of neurons. So this is the neurons. Here you see all the different processes of the neurons. And then the way we are using in order to influence the neuronal activity by using light is to use optogenetics. So this is a technique that was proposed by Desireux in 2005, by which you insert photon light-sensitive proteins in the interface of the neurons, and by shining blue light, you activate those proteins in such a way that the ionic channel at the membrane of the neurons opens, so that the electrical activity of the neuron is activated. And so in this way, you can use light to activate the neurons. And so the experiment we did was to take a culture of neurons, and then by using pattern light, try to write a given circuit into active circuit into the neuronal culture. And so here is an example of the experiment that we did. So here you see an optical microscope image where you see the neuronal body, all the different processes. And then by using pattern excitation, so we shine light on 4 different neurons. And by doing that, so we were able to activate the specific connection, the specific circuit that links this neuron to nearby neurons. And so by using this pattern light illumination, so what we are able to do is that to write a given circuit within the neuronal culture. And so in this way, so we are able to make a biological culture and activate this biological culture by using light. And now the last point in our research is to try to merge those 2 fields together. So on one side, the photonic integrated circuit, on the other side, the biological culture. And so the setup that we are using is the one shown here in this image. So we have a bunch of optical fibers that are coupled through a fiber array to a photonic circuit. And what you see here is, for example, the fact that we are sending blue light on one fiber, and this blue light is propagating in the photonic circuit. And now in the photonic circuit, by using grating couplers, so we are placing in given a position, so we are placing a scatterer. So place points where the light is scattered out from the circuit and then is sent to the neuronal culture. And then we grow neurons on top of this photonic circuit. We place the hybrid neurons and photonic chip under the microscope. Here you see the actual experimental setup where you have all the different optical fibers used to input the light in the photonic circuit. And then here you have an optical microscope that allows you to see whether the neurons are active or not. So here is the first experiment. So where you see the neurons that have been grown on top of the photonic chip. Here you see those small gray structures that are the actual neurons, and then you see the black line here, so the dark green lines that are the lines where the photonic waveguides have been produced. Then we look whether the neurons are alive, and so we put the neurons under the microscope, and you see the blue light that is coming out from the neurons because of the presence of chromophore that when you excite, so they shine. And then we turn on the light in the photonic chip, so we insert the light through the fibers, and then we have all these different points that are the different scatterers that scatter the light out of the chip, and this light should be used in order to excite the neurons. And indeed, so what you see here is a composite image where you see the neurons, the green structure. Then you see the blue dots that are the blue light that is scattered out from the photonic circuit. This light is absorbed by the light-sensitive proteins, the channels open, and the neurons start to be activated. And the red spot here shows the fact that the neurons start to be activated. If you compare, so you see without the light, the blue light in the photonic circuit, no red spot, and with the blue light in the photonic circuit, you see the red spot. And if you blow up, you see indeed the fact that the neurons are indeed activated by the blue spots. And then what you can do now is to draw the culture on a matrix of electrodes, so the neuronal culture on a matrix of electrodes, in such a way that now you can also record the electrophysiological activity of the neurons. So you can read what the neurons are doing in real time. And so in this experiment, what we did was to stimulate the culture by using pattern light. And then we could measure the electrophysiological signal by this array of different electrodes that are the dark spots here. And this is the outcome. So whether either we do illuminate the full area of the electrodes, you see the different recording, which means that the different activities of the different cluster of neurons that are detected by each electrode here in this array. And when you do excite locally by using a spotlight excitation, so you see that in this case, you only excite the network of neurons that are connected to the cluster that you are exciting. And so here I'm showing you that these hybrid artificial biological networks and the data that we have collected paved the way to our vision to be able to integrate and build a hybrid network of artificial and biological neurons. Still, there is a long road ahead in order to move from the in vitro experiment that we are doing to in vivo experiment and eventually to humans. Because at the very end, so what we are trying to do is to use this hybrid circuit in order to support malfunctioning brain sectors. Because in this way, by using these hybrid circuits, so we can teach our circuit to perform, to make and replace some function that a human brain is not able. And so we foresee application of this circuitry in the neurological diseases. By saying that, I'm finished. So I would like to thank the European Commission that through different projects is supporting this activity. And I'm ready if there are any questions. So thank you. Hello.
Hi, thank you, Dr. Pavisi, for the insightful presentation. So now we'll move on to our Q&A session. So just a reminder that if you have any questions for any of the speakers, please type down in the Q&A box and they will read it out loud and answer them. So I remember the first question we have is for Dr. Patrice Genevet. So Doctor, the question is for you. Was the thermal effect on optical results such as reflection, etc., considered and analyzed?
Yeah, so thank you, Majid, for the question. No, we didn't characterize this temperature dependent response. Obviously, like it depends of the material response, you know, as a function of temperature. So you do have indeed refractive index change as function of temperature in the materials that are generally used in optics. That being said, you know, the change within the reasonable temperature change, the modification of refractive index is generally small. At least it induces a relatively small change of the spectral response of this nanophotonic structure. So you would not expect to have a huge modulation if you are dealing with a classical structure. Yet, it's possible to use the same process as what has been discussed by Lorenzo today, which is to use the temperature-dependent response of the material to induce tunable response of this nanophotonic system, but these are generally very small. And so you have to work in let's say, highly resonant system. And it is possible. We have a paper that has just been published in Laser and Photonics Review, where we have been calculating essentially the response of a Gir-Tournois resonators, very high reflection coefficient Gir-Tournois resonators, so that works with very high Q response. And indeed, it is possible to use the temperature dependent of the silicon as a tunable knob, essentially for controlling the phase and the reflection properties of metasurface. So yes, I invite you to actually take a look in Laser and Photonics Review this month. It's a paper, it's called Universal Modulation of Light with Metasurface or something like that. So it is possible, but it requires very high Q for really being able to leverage on thermal effects for modulation of light with metasurface.
Thank you so much. So that's all the questions we have for today. So I will just wait for a few seconds. So if you have any questions, please type them down. If not, just a gentle reminder that if you need a certificate of participant for today's webinar, you can email me with your name. So I've already typed down my email in the chat box. And also just a reminder that the recording will be uploaded to the webinar's website. So there will be a follow-up email sent. So if you would like to refer to both speakers' presentation, you can wait for that email and watch the recording after.
Exactly, and don't hesitate to send any question by emails. We'll be happy to answer. I mean, I'm guessing, right, Lorenzo?
Sure. No
Yeah.
problem. So you can find also the different links to the different papers and reference if you are interested.
Yes. If you have any questions for the speakers, you are welcome to send the question to my email and I'll forward the questions to the speakers accordingly. Yeah. If there's no more questions for today, then we will end this webinar here. So once again, thank you for both speakers for joining us today. And thank you everyone for participating in this webinar and celebrating Day of Light with us. So thank you so much and see you soon. Bye-bye.
Thank you.
Bye.